talk about here is we're going to start a lot with the chemistry and understanding safety around chemistry. For anyone that's kind of been keeping up on really looking at 9540A, some of the stuff coming out of there with that testing from UL and understanding really what it takes for a lithium battery to be safe and what the differentiating is between lithium chemistries. So within lithium chemistries, we see a ton of different types of chemistries. We've got lithium iron phosphate, which is what SimpliPhi uses. NMC, really popular still in cars. You definitely see it in some of the bigger name batteries still using it, but they're also slowly migrating away from it these days. And then some other, not as common for what we're talking about batteries, but you can see the common theme for all these other batteries on the right here is cobalt-based batteries for the most part. It's going to be important for what we're talking about today. Really, there's a lot around understanding why the cobalt-based batteries are a little bit more temperamental when it comes to safety, thermal runaway, versus something like a lithium iron phosphate battery that is not as kind of volatile. And you can kind of see that laid out here in the chart regarding danger of thermal runaway, ventilation requirements, cooling systems, safety monitoring equipment. And again, we'll talk about all of this as we go through. So just to reiterate, chemistry-wise, SimpliPhi uses lithium iron phosphate with a cylindrical form factor. This is our chemistry. And a lot of what I'm talking about today related to safety and chemistry is going to be around the difference between that and cobalt-based lithium batteries. We'll also talk a little bit about lead acid, but that's the majority of it. So what is thermal runaway? Thermal runaway is when a battery or cell becomes hot enough that a chemical reaction begins generating more heat and further accelerating the reaction. It can cause off-gassing, fire, or explosion. I think we're all pretty familiar with this concept at this point. I mean, if you've watched the news, thinking about even like a car, like an EV car, I won't name the specific brand, but I think we all know which one we're talking about, that, catching on fire and actually being very difficult to put out. What actually causes this? It's commonly caused by cell failure due to lithium plating and contamination during manufacturing. This causes a micro short circuit within the cell, but it can also be caused by external heat sources like an unrelated fire, internal short circuit due to puncture, or overcharging. Really anything that increases the temperature enough to become self-sustaining. We're going to talk about those kind of temperature thresholds, but again, this is kind of important when we think about batteries. We think about residential batteries is a lot different than when we might think about car batteries. Punctures and things like that are probably a little bit more common when we're talking about like a car battery catching on, going into thermal runaway. But there's still a lot of safety factors, and those micro short circuits definitely can occur. If there's any chance at all, it's always less than 0%, as they say. So it will eventually occur out of every now and again out of batteries. So that's where it really comes down to what chemistry is being used and how does that battery go into thermal runaway. So looking at temperatures, during thermal runaway, and only during thermal runaway, electrolyte will vaporize, actually, creating a flammable gas. If the gas is contained in the cell, the gas will not ignite. If the gas escapes, it is toxic and flammable. It's also a lot of where that propagation comes from, where there's a lot of batteries that are catching after another battery. So kind of this chain reaction of a lot of batteries catching from a single battery, seeing some sort of micro issue. So that's kind of where it comes down to, where we want to talk about propagation is, if one cell catches in a lithium iron phosphate battery, we don't see that big propagation where it starts to spread very rapidly and very quickly, where we do with the NMC. A lot of that is around the temperatures too, and just the chemistry itself. So LFP can reach a higher temperature than NMC and other cobalt-based chemistries before thermal runaway actually begins. So LFP, just looking at these ballpark figures, so don't quote me on these. They're rough. They're not exact. 200 C for lithium iron phosphate, and 170 C for NMC. LFP reaches a much lower maximum temperature than NMC and other cobalt-based chemistries during thermal runaway. So this is the max temperature when it actually goes into thermal runaway. LFP around 400 C, NMC around 675 C. And LFP also releases less gas than NMC and other cobalt-based chemistries during that thermal runaway. So takes more heat to actually ignite it, and it burns. It doesn't burn as hot. Is the kind of benefit of LFP versus NMC there. Sorry, there it jumped. So just kind of looking at thermal runaway and impact on cell chemistry as far as temperature goes. So we can kind of, I know it's a bit messy here, but we can follow this chart and actually see the temperature and the heating rate. And that's really done by temperature over minutes / amp hour, or minutes and amp hours. So really kind of temperature over energy. And looking at this chart, we can kind of follow the different, oh, looks like we got a few. I'm just make sure everyone's seeing okay. Oh, somebody's saying they cannot see the video. Daniel, I see you're on. Can you confirm that you're able to see the video? Okay. Miguel, I think that's a problem on your end. I would maybe try logging in and logging back out or adjusting the settings, but it looks like everyone else is able to see it right now. So just if you want to jump on. Okay, yep, looks like everyone else is confirming. So I apologize for that. I'm not sure what's going on. All right, so back to the chart, we can see LFP. Obviously, the curve is a lot different than we're looking at the NMC stuff, or even looking at the other lithium chemistries that we might not talk about as much that still contain the cobalt. The difference in runaway profiles are actually related to oxygen release and combustion at different cathodes. And I won't talk too much about that, but that is really where that cobalt plays such a big part. So looking at safety systems, this is really where there's a lot of differentiation between the batteries. Maintaining a safe operating temperature for the cobalt-based lithium batteries actually requires ventilation, cooling, and thermal monitoring equipment. So that's something that's really specific for cobalt. We do not require that in the lithium iron phosphate batteries. They don't have that kind of external equipment. And really what that does is it adds cost and a point of failure. It's also a parasitic drain on the battery's capacity. So it actually is using some of that battery capacity to actually operate. SimpliPhi batteries have a wider operating range than cobalt-based lithium batteries. Therefore, our batteries require no ventilation, no cooling, or thermal monitoring equipment. So that's a great win. I mean, it's a lot less, and we've kind of validated, we've definitely validated this through the 9548 testing, where we don't need that external equipment to keep the battery safe. And we cut down on costs and points of failure that way. Looking at lead acid comparison, let's talk about thermal runaway and lead acid. It's a little bit different. So if we're looking at VRLA, they can experience thermal runaway, but it is not an exothermic chemical reaction. It's actually caused by initial increase in temperature. As a lead acid battery gets hotter, it will accept more current from charger. If unregulated, basically the temperature and the current continue to rise together. It ends when the electrolyte is actually burned off at around 125 degrees C. So it is possible. It's a little different though when we're talking about lead acid batteries versus what we talk about with thermal runaway on the lithium side of things. Off-gassing occurs even during regular charging. We all know this that have worked in lead acid batteries. Hydrogen is produced, which is explosive if not vented. I can't tell you how many systems I've seen in my day of bad battery boxes, bad designs, no vent fan, maybe the inverter equipment's too close to where that off gas is happening if they are flooded cells. And overcharging actually causes hydrogen sulfide, which is both toxic and explosive. And we'll also talk about mining a little bit. Lithium mining is mostly environmentally benign, but that does not, and we'll talk about this, that does not mean that it is good for us more than anything. And we'll kind of get into that. It does not involve pickaxes or headlamps in tunnels. Water is actually pumped through a mineral salt bed underground and into a large pond. Sun evaporates the water, leaving minerals and salt behind. So lithium, iron, and phosphate are fairly abundant resources. All of these are non-toxic and do not involve child labor, unlike cobalt, which we'll jump right into. So cobalt comes primarily from the Congo. It's very, very similar to what we would kind of look at as the diamond trade. This is why when you get a cobalt battery, you can most likely assume that there might not be the best practices as far as humanitarian stuff goes, how that cobalt was actually mined and supplied. Some plants highly mechanized, others digging with hand tools actually. And it's estimated 1/4 of cobalt in DR, in the Congo, comes from black market with zero regulation. Even the regulated mining is subject to serious corruption from political leaders. So again, it's really something that we can make similar to the diamond trade. When we're talking about cobalt-based batteries, it's very, very similar there. And by cutting out the cobalt and using lithium iron phosphate, we don't basically support these practices. Okay, let's talk a little bit about battery safety standards-wise. Just looking at standards, FAA and air shipping is actually a really important one to kind of think about. Since 1991, 206 separate incidents occurred involving the combustion of lithium batteries on airlines. SimpliPhi has actually received special permission from the FAA to airship globally. So this has been since I've been with this company, we've had permission to actually fly after being able to prove the lithium iron phosphate chances of thermal runaway and fire propagation are not the same as cobalt. And this will continue to expand as 9548 kind of takes hold. And more people are kind of aware of how it's different than the chemistries are actually different. I won't talk about 38.3. It's really related to the batteries and shipping. UN 3480 is related to packaging, which I have to always put out the little note here. If you're working with our batteries, keep your original packaging at least for some time, or keep the original packaging of maybe one set of batteries so that you have it handy. It's already set up for that 3480, and it's a really big pain if you're just your own person trying to ship back a battery or anything like that, to actually set up that kind of those standards with the correct hazmat labels and things like that. I like this picture on the side. A note that has actually experienced thermal runaway. I've actually had laptops that have done that to me. Never a cell phone, luckily, because mostly sits in your pocket, but I definitely have had laptops go swell and the battery actually catch from there. So again, that's really common in cell phones and laptops, which are mostly polymer with some cobalt typically based batteries. Now we'll talk about 38.3 and what that testing actually is. So basically, let's look at the 4 different things that it goes through. Altitude, so it's actually stored at very low pressure. This is related to the battery actually going through this test. Simulates high altitude. Thermal, cycling between 72C and -40C in rapid succession. Vibration, 36 hours of intense vibration, simulating transit, which is really important when we talk about a battery arriving on site after being shipped out from a company and how that's going to hold up. So when we're talking about cobalt, for instance, we talk a lot about the safety measures. Well, there's these safety redundant systems in the battery that could see major issues if things come loose during shipping. And the same with shock, 18 impacts simulating repeated drops or crashes. So to pass this test, you need no leakage, no venting, no disassembly, no rupture, and no fire. Open circuit voltage of each battery directly after testing, not less than 90% of its voltage prior to each procedure. That's how you pass this test. And that's where we get this certification from. And then actually looking at, there's actually two more I forgot here. External short circuit, battery heated to 57 degrees Celsius for 6 hours. Then terminals are short circuited until a maximum temperature is reached, and then cool down occurs. Must not exceed 107 degrees Celsius and not catch fire to pass, as well as overcharge twice maximum charging current and 1.2 times max charge voltage, must not catch fire to pass. So, when in the field, it's pretty hard to mess up a system enough where something like this occurs when there's not that chance for micro issues. So in the lithium iron phosphate, for instance, it can't just simply catch on fire. It just does not do that. So something like overcharge has to really occur to get that temperature up. And as you can see here, it has to be higher than twice the maximum charge current. So that's pretty high if we're talking about what might catch a battery on fire. It's a pretty big misstep on a system design. And looking at UL, we all know UL is a third party which creates testing standards, performs testing, and certifies products. Battery-wise, 1642 is the cell level, 1973 is the battery level, and now 9540, not to be confused with 9540A, is the actual ESS energy storage all-in-one certification for batteries and systems together. 9540A is a separate test protocol, and we're going to talk separately about that, but I've mentioned it a lot. That's a test protocol, but not an actual certification. UL certifications are needed for permitting, fire codes, electrical codes, and building codes. Insurance purposes, absolutely. Ensuring the safety of your home and family, and time of sale inspection. So you definitely don't want to buy a battery that doesn't have these different certifications, including 9540 really at this point, which is becoming more and more stringent where people need that listing. So again, 1642 relates to the cell level. And this really tests for things like shock, vibration, drop, heating, temperature cycling, low pressure, short circuit, heating, forced discharge, crush, impact, and humidity. 1973 is that battery level, where we can really kind of see how when the batteries all put together, the testing there. And then 9540, how the system interacts, could be with a charge controller, with the inverter, with the battery, all in one, maybe in an enclosure. It doesn't actually need to be, but how those interact with each other for a little bit extra safety. Now we can talk about 9540A, which is actually the testing. So this test method is not a certification. Basically, and I'm going to kind of go off script here and just talk about what I know as far as what we went through as far as the testing goes. The testing really starts with the battery level. The cell level is a little bit there, but mostly it starts with battery level is the most kind of first important step, where basically 7 cells within the battery are heated to thermal runaway. They're forced into thermal runaway, and then we can see how the fire propagates from there. Then it's done on a system level, where it actually is done basically with the system itself and not just, sorry, I jumped ahead there, not just the battery. And again, we see how it propagates and where things might catch. And there's even walls that are measured with thermocouples that actually take temperatures and exactly tell you, hey, did that wall get too hot? Or if it was in a home, it could be dangerous. So our test came out great with the lithium iron phosphate batteries and our design, where basically it was shown that even when forced in a thermal runaway, there was no propagation, notable at least, where it didn't spread. It didn't spread outside of the battery. And then when it did get hot enough to kind of show some sort of impact, we had, I think, 12 batteries in an enclosure. It only kind of heated the batteries next to it, but didn't actually catch the enclosure on fire, even when forced into thermal runaway. And the wall behind it had no notable change that would be dramatic as far as a fire safety hazard. Some of the cobalt batteries that are going through this are seeing that they actually need to add now extra safety equipment to meet this standard. So again, 9540, the listing itself includes UL 1741 for the inverter and 1973 for the battery, whereas UL 9540A just informs the parameters of the battery safety install conditions. So that's how the two kind of go together. UL 9540A does not currently affect 1973 and UL 9540 for the first edition, but it is going to be going in as more of hey, this is a reference to the safety of the battery and what safety equipment might be needed. Certain regions are calling for that test already, New York being one of them, where basically you might get an inspector at AHJ asking for that that testing, the UL 9540A testing, and that's something we can provide direct to the AHJ so that the installation can go through. Looking at disposal, here we see a fire at the recycling plant. This recycling plant in Cincinnati, a general materials recovery facility, experienced 6 fires in 2016 alone due to consumers disposing of their batteries improperly. Our batteries are technically landfill safe and recyclable, ROHS compliant, so no toxic chemicals, which would be lead, cadmium, mercury, and this is not really related to cobalt here, but this is just the listing that we're talking about. But again, as far as disposal goes, my go-to when it comes to disposal of batteries, if need be, is contact the manufacturer first. If you contact us directly, we can lead you to the right place, the people that we know that can actually recycle these batteries, and save you a lot of time and save resources like this where a fire happens due to improper disposal. Okay, moving on to a little bit of installation safety. We're kind of reaching the end here. I know it's a pretty quick presentation, so we're just going to wrap up here. We're going to talk a little bit about just installation safety guidelines. Can't stress this enough. Hire a professional when in doubt. I mean, even sometimes as an installer, I've had to hire an outside professional for products that I'm not aware of or haven't used before. So it's never a bad idea. Always check your wire sizing, breakers, and fuses. I've seen wire sizing cause fires and other sort of damage plenty of times, as well as sizing for the battery. I mentioned, that double over discharge, basically how much of an overcharge we would actually need to force a fire to happen. If you stick with the guidelines on sizing, you will absolutely never experience something like that, and you will not run into that issue. If you're kind of unsure, we've got a ton of tools for product documentation as well as sizing guides in that documentation that goes through the right sizing. But again, our sizing guidelines are directly related to safety factors as well to make sure that nothing like that ever happens. As far as PPE and tools, all batteries, you want to use gloves in a dry environment, insulated tools, safety glasses. I can't tell you how many times I see people not using insulated tools on batteries, which is pretty terrifying. Calibrated torque wrench is actually something I always like to mention. I tell you how many times I see people jumping from battery to battery, not calibrating torque wrench between job sites and things like that, and over torquing batteries. Obviously, voltmeter and amp clamps, never a bad idea. For FLA, acid resistant aprons, boots and gloves, face shielding goggles, spill kit. So as you can see with the FLA, with the lead acid, we definitely have a lot more safety requirements. I should jump back. I mean, I've definitely worked, when I work with lithium versus lead acid, it's really kind of a big difference when trying to, handle those batteries and the toxic chemicals. As far as installation and commissioning goes, breaker off during installation. I know that's just a stupid thing to say, but I can't say it enough. And also very careful, not just short terminals. I've seen this a lot. It's something that's very hard to come back from. Never connect 2 batteries at significantly different SOCs. So state of charges, that's always a good idea. Voltage is not always accurate indicator of state of charge, especially when adding to an existing bank. So if you have a bank that's been in commission for a while, just be sure that you know where the state of charge lands before kind of mixing in the batteries. It can be a safety issue. And order of commissioning: turn on the batteries, connect to charger, program charger, then connect power source. whether that's PV, gen, or grid to charger. And definitely fully charge before powering loads. That means fully charge the batteries before powering loads. All right, that kind of wraps it up. I'm just going to mention briefly for anyone that's on the call, if you're installing our batteries and interested in becoming part of our IQ program, takes about 10 minutes. Follow the link there. We actually offer rebates now for this program, $25 per battery when you sign up for every install you do, as well as a photo contest for best install every month that wins about $250. So if you are already installing our batteries, definitely hop on this link and check it out. All right. Looks like we don't have any questions today. So if there are any further questions that you think of offline, you can always email me at training@simpliphipower.com. We're happy to answer anybody's questions. Thank you, everybody. Appreciate your time.